In this example, we're given the set of Chebyshev's polynomials. We're given the first three. So our set is for s equals 1x and 2x squared minus 1. So the Chebyshev's polynomials have the norm over the interval from -1 to 1. The TIs, which are the polynomials, TI times TJ. And so we want to, that's the norm for this particular one. And so we want to use the Gram-Schmidt orthogonalization to create a perpendicular or an orthogonal set. So to do so, we're going to set U1 or U0 to keep in terms with the notation here. The vector, first vector is going to be U0. It's going to be T0, which is the one here. Okay. And then likewise, we're going to have U1 is equal to our second vector, T1, and U0, E1, the inner product of U0 and T1 divided by, so you should be fairly familiar with this by now, but divided by the norm of U1 all over, or being that weight, if you will, times the vector U1 multiplying and then subtracting out. And finally, we'll do U2 is equal to T2 of X minus the inner product of U0 and VTU2 divided by the norm. And then again, that weight being multiplied by U0. And then also for U1 and T2, and then the weight of U1 and subtracting those components off. So to compute all of the different integrals and also to simplify everything, we'll utilize technology. So we'll switch over to that now. So for this one, we set T0 equal to 1. That's our first vector. Our T1 of X is equal to X, and our T2 is equal to 2X squared minus 1. So following the Gram-Schmidt process, okay, we set T0 or U0 equal to T0, so that's equal to 1. And then here, I'm using the simplify command just to kind of hopefully make it a little bit more readable. So U1 of X is just like we saw, this is T1 of X minus the weight of U1 and the integral of U1. This is the norm, the inner product, and then the norm of U multiplied and subtracting off. Okay, so that gives us then just X. Turns out that this integral is 0. So this whole thing is 0. So it's just really T1 of X. Okay, and then likewise for U2, we have T2 minus the inner product of U1 and T2 divided by the norm of U1 or U0, and then times U1, U0, and then we have the inner product of U1 and T2 divided by the norm of U1, and then times U1 itself. So this again will be 0. This term here is 0 divided by 2/3 times X. So this term is actually 0. And this term looks really complicated. You can kind of see it. So what I did is just to verify, I pulled over the computer algebra system in GeoGebra and had a numeric look just to simplify all of this. And it turns out that it is what I thought, which is 2x squared minus 2/3 x. Okay, so that verifies then that our values are expected as expected. And now we're going to check to see if the actual products or vectors, if you will, are in fact orthogonal. As expected, if we look at with respect to the norm, U0 times U1 gives us an integral, gives us a norm of 0 or an inner product of 0. If we look at U0 and U2, it gives us an inner product of 0, and then the last one, U1 and U2, gives us also an integral of 0 or a norm of 0 or an inner product of 0, sorry. So indeed, it shows that for our set, we have orthogonalized the matrix, the set S with our Gram-Schmidt process for U1, U2, and U0. All right, I hope that was helpful, and I'll see you in the next video.